We keep talking about ideal gases. What about real gases? What makes an ideal gas is that there are no attractions between the gas particles, and there's negligible particle volume. There are certain conditions under which this is not true for real gases. At STP, if we calculate the molar volume of different gases, this would be the ideal gas, 22.41 liters. We see these other gases, chlorine, carbon dioxide, ammonia, nitrogen, helium, hydrogen. Their molar volumes at STP are very close. In fact, helium is exactly to 4 sig figs is the same as an ideal gas. Because at STP, the volume of the particles is negligible and the interactions between the gas particles are also negligible. But if we get to a high pressure or a low temperature, then those things are not true and we see deviation. So what happens? So here is low pressure, the molar volume, almost identical to an ideal gas. When we decrease the volume, increasing the pressure, now the argon atoms, their volume as a percentage of the entire volume is greater, right? And the size of them starts to become important. So, we think about the classroom, there's a lot of people in here, but, if we switched everybody out for, O-line and D-line football players, they'd still fit just fine, right? Or if we switched them out for kindergartners, it'd be fine. What if we were in an elevator? We had 10 people in the elevator over there. Now it matters, right? The 10 football players, that might be a squeeze. 10 kindergartners, plenty of room. The smaller space, now the volume of the people matters. Same thing with the gases. That make sense? Real molecules do take up space. So the molar volume of an actual real gas is larger than for an ideal gas. And so here, looking at argon, at STP, down here at like normal stuff, they're like right on top of each other. But as we go to higher and higher pressures, and these are really high pressures, 800 atmospheres, that's a lot of pressure. They're squeezing those guys together. And now we see that the molar volume of argon is higher than ideal because the particles are taking up volume. So, how do we calculate things for a real gas? Well, Johannes van der Waals modified the ideal gas equation. So the volume got bigger, so you can add a term to account for that. So it's got this constant, the van der Waals constant, which is different for different gases because their molecules are of different sizes. If we look at high temperatures, pressure of gas is nearly identical to that of an ideal gas. Because gas particles at high temperature have high kinetic energy, they're moving fast, and so any attractions they have to each other really don't matter. So if you think about men and women or just people passing on a New York City sidewalk, everybody's walking really fast, there's lots of people, you might think, ooh, that person was attractive, but do you get into a relationship walking past people on a sidewalk? There's no time, right? Well, what if you put a bunch of those people in a speed dating situation? I mean, still not a lot of time, but you've got like maybe 5 minutes together or something. Because there's more time, now there's a chance for an attraction to form, right? When we get to low temperatures, the gas particles are moving more slowly, And as they run into each other, it's more like speed dating, and they're like, oh, I kind of like you. Oh, I have to leave. But it slows them down, right? So there's less kinetic energy, and those attractions can become significant. And that leads to the actual pressure being less than what would be predicted. So that would look something like this. Here at high temperatures, the pressure is the same. At low temperatures, we see the pressure of the real gas is lower than that of the ideal gas. And van der Waals, made an adjustment for this too. So the pressure gets smaller, so you have to subtract something, minus A times N over V, the quantity squared. V is the volume, N is the moles of gas, and here's another constant. So you put both of those constants together and you get the van der Waals equation. Yuck. We're not going to do anything with it. We're going to just use the ideal gas law, PV equals nRT. That's pretty friendly compared to this, right? If you would have to use this, you would look up these different constants depending on what gas you have, and you'd throw those in there. Most of the time, we can just ignore it. If we plot pressure times volume over R times temperature versus pressure for 1 mole of a gas, an ideal gas will give us a straight line. Real gases are going to vary. Some of them are going to be higher, some are going to be lower, some are going to start out low and then get high. So what's happening here? Not getting high. You guys. So the ones that are above the line, the factor that's more important here is the volume of the molecules. And for the gases whose curve falls below the line, what's more important is the attractions between the particles.